Hello, we are Team 9. We were in charge of developing an instrument we call Gurdytron, a digitized hurdy-gurdy. Our team consists of 4 members: Brody Brooks, Joey Bell, Andy Miller, and Nate Pitts. You may be asking yourself, what's a hurdy-gurdy? And we don't blame you for not knowing. Its main features are the crank and wheel. The musicians turn the hand crank and in turn rotating the wheel. The wheel rubs against some strings and causes them to vibrate and make notes, similar to how a bow works on a violin. It was popularized during the Renaissance and is starting to rise in popularity again thanks to some modern media and games such as Sea of Thieves or the soundtrack in the God of War games. While it is a unique sounding instrument, it does not have some modern capabilities that other instruments such as pianos and guitar have: MIDI interfacing. Our goal is to add this to the instrument to allow it to connect to digital audio workstations, also known as DAWs, as we will call them for the rest of this presentation. This would enable the musician playing it to have a silent instrument to practice or play while keeping the feel of the original instrument. It would also allow some fun features like using filters in digital audio workstations or pedals like we will have at our table in the upcoming Tech Expo.
Using our $2,000 budget, we looked to create a device that would output MIDI signals based on crank rotation and which push buttons were being pressed. This device would be an input to a DAW, or digital audio workstation. This project was done in 6 gates to keep our progress on track. Gates 4 through 6 were our focus of this semester, leading to the finale of the project at the Tech Expo. Here you can see our electrical design and a drawing showing the final assembly. It's a lot to look at, but it's really quite simple. The main feature of the electrical schematic is the Arduino Leonardo, chosen due to its size and native USB capabilities. Connected to the analog and digital inputs are the systems for the 2 main functions of the instrument, the keys and the crank. The wiring for the keys is shown on the left side of the Arduino. We use pull-down resistors with our limit switches to take the place of the traditional keys. These inputs were wired to the digital inputs of the Arduino, mostly. We use digital interrupts for the encoder in our program and only select pins on the Arduino that are capable of this. That's why most of the keys are on the digital inputs, with 2 others moved to analog inputs. On the right side of the Arduino is our encoder, used for tracking crank rotation, direction, and velocity.
To achieve the functionality and aesthetics of the hurdy-gurdy, we needed to design and manufacture many parts. For the design aspect, we used a CAD software called Inventor, and for the manufacturing aspect, we chose to 3D print all of the parts out of PLA wood. For the digital hurdy-gurdy, we chose 12 buttons for different notes and 2 additional buttons for octave up and octave down. These buttons are designed and integrated into the neck of the hurdy-gurdy, which are printed as an assembly. For the rotational function of the hurdy-gurdy, we chose to design a lever crank which press fits directly into the rotary encoder shaft. The last couple of parts that make up the hurdy-gurdy are the body and the base plate. This is where most of the electronics, like the microcontroller, will be mounted.
Now let's see how all these systems work together. The first thing to check is something fundamental to hurdy-gurdies, the drone strings. On our traditional instrument, because the strings are always in contact with the wheel, whenever the crank is turned, some notes will be played on the drone strings and bass tuning of the melody strings. When we turn the crank, you can hear 2 notes being played. These are our drone strings. You also probably noticed the volume slider for the channel this instrument is going on, up and down. This is another feature of the traditional instrument we brought over. Depending on how fast the crank is rotated, the sound of the instrument changes. It does change pitch slightly on the traditional instrument, but we focused on the volume changes present with different velocities. Next, we'll turn our attention to the keys. The original hurdy-gurdy has 24 keys, or 2 full octaves. We only have 12. That's where these 2 buttons come in. They are octave up and octave down. These allow us to raise or lower the octave of our 12 notes that are currently on the instrument. This allows it to play more notes than the traditional one is typically able to play while using less keys. Let's take a quick peek at this. Yeah. In the top left of FL Studio, our chosen DAW, you can see what note was being played. If we press the octave up button and play that note again, you can see it's exactly 1 octave higher than it was previously. Now if we press the octave down button, it's back to its starting point. And one more time down, it'll be an octave lower. And then all the rest of the keys just going up the scale. And that was our full octave. Now, like any other stringed instrument, only the highest note being played at any given time is actually played. So you can hear the higher note is being played, but the lower one turned off and will not turn back on until the higher note is let go of. The instrument is not capable of playing more than one melody note at a time. Additionally, the notes are only played when the crank is being turned. Pressing a button while the crank is still does nothing.
This was an overview of the problem we tackled over the past 2 semesters. As we demonstrated, the Gurdytron successfully connects to a DAW and sends commands based on actions performed in accordance with the original instrument. We demonstrated its functionality in FL Studio, but this will also work in other DAWs. We have successfully tested it with GarageBand, so it should work with varying quality of DAWs. If you'd like to learn more about how the Gurdytron was developed, or have any questions, or just want to give the crank a quick turn, we look forward to seeing you at the Tech Expo. Thank you for listening to our presentation.